Okay.
Okay, good morning. So today will be the course. That's because you already know the background or the material of linear algebra. So we're going to solve systems of linear equations. We will assume for this recitation that we have n linear equations with n variables. And of course, the coefficients of these linear equations are constants or non-constants. These are the eighth here. And the, the answer of each equation is also a non-constant. These are the b's. You know that we can reformulate this set of equations as a matrix of constants multiplied by the vector x equals the vector of t. A is called the matrix of coefficients or the coefficient matrix. The x is called the variable matrix or the variables matrix or the not the matrix vector or the solution vector also because we want to solve it, right? And the b is called the vector of constants. Here A is square matrix. That's because we're talking about n equations of n variables. And we will assume in this recitation for now that A is invertible. There is a solution. There is a unique solution for this set of equations because A is invertible. So that's our assumptions.
So there is a single solution.
Or it's unique. Okay. And the next recitation we'll talk about matrices that are not square. But we'll generalize in some way our methods here. And we will talk only about the Gauss-Jordan or Jordan elimination method or algorithm. We will not implement it in coding, but we will say how to do it. Okay. So you know mathematically this set of equations is solvable by finding a minus 1. That's because a is invertible. So there exists a matrix a called a minus 1, such that a minus 1 multiplied by a is the identity matrix I. And we take the equation ax equals b multiplied from the left by a minus 1, and then x equals a minus 1b. So that's the solution. So in order to find the solution, we somehow have to find a minus 1, or that we won't find a minus 1, but we will find a minus 1b immediately. Okay, so that's our way for now. We'll find a minus 1b immediately. And how do we do that? Gauss-Jordan method or elimination method or process. How do we find the solution of this equation?
Manipulate A until it's the identity matrix.
Yes, we use the.
And we do it
We want to get to a reduced form of the matrix by using some elementary operations. But at first we we define the augmented matrix A tilde to be the matrix A concatenated with the vector B at the end of it. So that's our augmented matrix, the matrix of n times n plus 1, because it has n rows, but n plus 1 columns. And we do basic operations or elementary operations on this A in order to get to a reduced form of it. But we can stop in the middle of the process and then choose what to do. So we can get to the reduced row echelon form of the matrix A, which is the form of upper triangle matrix, and then decide what to do. Okay, we'll talk about. So we can make the whole process of elimination and get to I here, the identity matrix, and if we get to I by the elementary operations that we talk about, this will be what? X or the solution or A minus 1B, provided that when we do the operations on A, we do them also on B. So we do the operations on the rows, say. And what are the operations that we are allowed to do? We can replace a row by itself multiplied by a non-zero number plus a linear combination of other rows. Okay, and this operation, which is operation number one, is the composition of two basic operations. One is to take the row and replace it by itself multiplied by a non-zero coefficient, and the second one is to take the row and to add to it, to replace it with itself plus a linear combination of other rows. Okay. This operation, this is the operation that we will use at first in order to get to the upper triangle matrix. And after that, we'll talk about the other two operations, which fall under the category of pivoting, and they are the replacement or the swapping between, or the interchanging between rows and columns. So operation number two is swapping rows, and operation number three is swapping columns. Now we will not use them. After that, we will use them. So for now, we will use only the first operation, but you know the third operation has a consequence, which is the change of the order of the variable. Yes. So if we change the order of the, if we swap columns, we also have swapped the variables corresponding to that columns. For example, if I swap between column 1 and column 2, this is the B, and I solve, and the only swap that I've done is this, the solution that I will get will be x2, x1, and then x3, x4. That's because I swapped between column 1 and 2.
You said like one way to solve it is to solve it until you left with only the upper triangle, right?
And then we will choose what to do. When I get to the upper triangle, I have two options. We'll talk about them.
Oh,
first option, to continue the process and get to the I.
Yeah.
Get to I here. And there's another option. They are, of course, equivalent, but they're not equivalent in terms of computation, in terms of cost. Okay. So let's write down our method by equations in order for us to know how to implement it in the computer. So at the 0th step, I take the first row and I do anything. Okay, so there is no step here. And after that, there was nothing. I take the other rows and try to nullify the first element in each. How do I do that? I take each row, and replace it by itself minus its first element divided by A11 multiplied by this one. Okay. And I do this for each row, for every row. So after this, I call this step number 1. Okay, and after step number 1, I get these primes. Okay, after step number 2, I will get here double prime. Okay, so after the first step, I get new numbers. I call them A primes, and these primes appear only in the second row and third and fourth. The first row I didn't do with it anything. So how do I write this? Say Aij prime, and I work with the ith row, so it is the ith row minus something multiplying the first row. Okay, and this is every element in the row decided or determined by the number of the column. And I take this row, for example, the second row, A2J minus A21, just this, divided by A11 multiplied. Yes. And of course, I do the same thing for the B's here. I take B2 prime, as I took everything here, I take it B2 prime and replace it by B2, I'm sorry, I take B2 and replace it by B2 prime, which is B2 minus A21 divided by A11 multiplied by B1, because I took this row minus something multiplied by this row.
Is this numerically stable? Because the subtraction here can be dangerous.
We'll talk about it.
Especially with the first element itself, you might want to set it to 0.
Yeah.
Not do the subtraction.
Yes. So we'll talk about it.
Can you explain again how did it become 0? How do you get the 0 elements?
You see the A21 there?
Yeah.
I take that row minus A21 divided by A11, the first row. So it's by definition, it by definition makes the first element 0. Okay. And that's step number 1. What is step number 2? To look now at this and try to nullify these numbers, this and this, at the third column. So how do we do that? For all these rows, we take each row and replace it by itself minus the first term in it, which is the second term in the column, in the second column, divided by A22 prime multiplied by this row. Okay, so it's like that I look at this matrix and do the same thing for it. Okay. So how do we write it? We write it like this. The ith row, I start with the third row, of course. The ith row is replaced by the ith row minus AI2 prime divided by A22 prime multiplied by the second row. Okay, and I do the same thing for this. And it always depends on, as you see, it always depends on the diagonal terms or the diagonal elements. So we used here A11 in order to nullify all of these. And now we use this term, which is on the diagonal, to nullify all of these. And it will continue like this. So we call this element the pivot, or the axis itself, the pivot axis. And we make this calculation n-1 or n-2 times, because at the last step I don't do anything. And then we will get to this upper triangle. 4. And when we get to this upper triangle 4, we have two options. One option is to continue. What do we mean by continuing? We continue using basic or elementary operations, what we did, in order to get here to 1, 1, 1. And how do we do this? We do the same thing, but starting from below. Okay, it's elimination. That's one way or one option. The second option is what? Again, it's equivalent, but we see here that we already know what is xn. Xn is this divided by this. Okay. So, huh?
Why is it?
Because the equation now is that this multiplying by xn equals this. That's the equation written here in this row. So xn is this divided by this. That's the solution. And after that, here I have only in the row before, I have only two terms equals something, but this term is multiplying xn that I've already known. Okay, so I call this backward substitution. And of course, it's equivalent, but it differs in terms of cost. So let's see an example at first. Here we have three equations, and we put them in this augmented matrix. And now I take this row plus 3 multiplied by this row, which gives me this. And then also in the same step, I take this row minus minus 2 times this row. And I get to this. After that, I will take this row minus this row. And in this way, I will nullify the second element. So I get to this augmented matrix. And this augmented matrix, if I recast it to equations, that it's meaning. Okay, this is the meaning of it. And therefore, I can say immediately x3 is 2 and plug it in here, find x2, and then find x1. Okay. So that's the two options that we have. And of course, we can also hold in the augmented matrix the A minus 1. For example, if I take the augmented matrix to be, if I take it to be A, B, I, and I do my calculations and get here after many operations to I, first elementary operations. Here, if I get here to I, this will be A minus 1B, and this will be what? A minus 1. Okay. So let's talk about this backwards substitution. And
What does the tilde mean again?
it's because another thing. This is the augmented matrix. So I call it tilde. And and here I have another augmented matrix which includes also this. I call it double delta. And what's the cause that I don't use this immediately? So it's also about cost. So if A is very, very big, I will use only this, not this, because this will add for me many calculations. And if I don't need them, so why for me to do it? I can. This is enough for me. And also, sometimes you you find a minus 1, and after that, multiply it by b. So what's better, to find a minus 1 and after that multiply it by b, or that we take this method, which means that we find immediately a minus 1. Okay, so you can think about it and see that if you get to a minus 1, it will have its errors because of the rounding, etc. And when you multiply it by b, you will have some cumulative errors, and this will be more accurate than taking this and multiply it by b. Okay.
Why you want to bring it to an alternative triangular shape instead of a canonic shape?
Because that's the midway. I can, after this midway, continue. And I can stop there and use this method of backward substitution, which costs me less in many cases.
That's an canonic solution.
Yeah. So if you want to get to I here, you of course cross the midway, and the midway is that reduced row echelon form. This is the midway, which has the upper triangle. So now, if we have this, if we get or achieve this, what do? First of all, we call all of them A's, okay, and then we have A11, A12 until A1n plus 1, and here we have ANN, ANN plus 2. And we start solving the equations from below, okay? So xn equals immediately a n plus 1 divided by a n. Okay? And after that, xn minus 1 equals what? So these are the equations. So xn minus 1 is multiplied, of course, by the diagonal term, an minus 1, n minus 1, plus the terms to the right of it, because to the left of it, the terms are 0, or the coefficients are 0. So we have only the terms to the right of it, which are the terms of the variables that we have already known or found. So here we have an minus 1, because yes, because we're talking about the n minus 1 row, n multiplying xn equals the n minus 1, the n minus 1 coefficient in the constant, or the, yes, in the vector constant, the new vector. And then xn will be dividing something by the diagonal term corresponding to it. And what do we divide? We divide the coefficient term, the constant term, minus the linear combination that is left. Here in the second row from below, it is only constituted or composed of xn. Okay. So when we talk about the first row, this is at the end of the process. X1 will be dividing something by A11. What's that something? It is A1n plus 1 minus this linear combination of the variables that we have already found. So we can build this recursive equation, or this recursive method, and say at first xn equals ann plus 1 divided by ann. And after that, for each I, starting from n minus 1 and then n minus 2 until 1, xi is the constant term at the last of the matrix, of the augmented matrix, a I n plus 1, minus the linear combination at the right of it, okay, divided by the the coefficient of the diagonal corresponding to. Okay, and we can write it like this. Okay, and here the xi's or the xj's are with I, starting with I plus 1 up to n, and we have already found the steps before. So that's how you can implement this way. And again, this costs me less than using the elimination. Because when you use the elimination here, you make the your operations on the whole rows. Here, as you see, I of course add many numbers, okay, but I don't do this for the whole row. So for each row, I make only one calculation like this, not like the reduction or elimination to get to the identity matrix. Okay.
So basically, if we only have a situation where we want to find the solution to a linear problem, or just one problem, there's a more efficient way to do it. But if I wanted to just find the inverse matrix for multiple problems, then I would want to actually find the inverse matrix.
Of course, if you want to find the inverse matrix.
But this basically allows me to find a solution without exclusively finding the inverse.
The inverse matrix, yes. And of course, I repeat again, if you have the vector b in advance or more than one vector b in advance, it's better for you to use this in terms of error than finding a minus. Because but finding a minus 1 includes errors, and when you multiply by b, you somehow accumulate these errors respectively to this. This has less.
But finding the solution every time is slower than just using the.
Of course.
Yeah.
But if you have in advance 3 or 4 or 5 p's that you want to find a solution for, and that's it, you use this and concatenate b1, b2, b3, b4, b5 here in the augmented matrix.
You can do everything together.
Yeah. Okay, so let's see here an example. So these are the equations. I put them in the augmented matrix, and then take this row minus this row minus this row minus the first one, and get to this. After all operations, we get to this, and we use our backward substitution. So x4 equals 4 divided by 2, x3 equals dividing by minus 1, dividing what? Dividing minus 4 minus 1 multiplying x4, and we continue. Okay. Okay, and again, if you have multiple b vectors, as we said right now, you can concatenate all of them in your augmented matrix. And what are the difficulties of this problem? Of this method? Sorry. The problems of this method, or the difficulties, are somehow close to each other. One is analytical and one is numerical, but they are close in their solution. The first problem is that we somehow assume that A11 is not 0. Okay? Maybe A11 is 0. And after we assumed that, we got to A22 prime and assumed that also it is not 0 and continue. So this pivot, we assume that it is not 0, but it's not necessarily the case. Okay, and if it's not the case, what do? We swap over. Okay, that's an analytical one. And the second problem is numerical, as we mentioned. If there is a small number, A11 is small, for example, and then we divide by it, we might have the problem of catastrophic cancellation. And so there, we can say it like this. If we divide by it, we will get a big number. This big number, if we add to it a small number, we will lose information about that small number. Right? And if we subtract from it also a big number, somehow close to it, we will lose also information or digits of significance. Yes, that's the catastrophic cancellation as we saw before. So let's see an example for this. You have here an example of two equations that the solution of x1 equals 10 and x2 equals 1, solve them exactly. Okay, so if you take x1 to be 10 and x2 to be 1, this is an exact solution. But let's apply our method. If we apply our method, and yeah, let's say for now that our computer is not binary. Okay, it is decimal, and it keeps up to the fourth digit of significance. Okay, so it's only because of that of us thinking in the decimal way, we are taking this. So of course, we can take the binary example, but let's think decimal, and let's think of our computer that it can keep numbers up to the fourth digit of significance. Okay, so what will it do? It will divide the second number by the first. That's the answer, but it will not have that number. It will have only 4 digits. So it will take this 0 to be 1 because of this 5. I use here rounding or rounding up. You can also think about cutting, not also. It doesn't matter. Okay, so this will be 1 or 0 in the computer, in our computer. So that's the number. And then the coefficient here, the coefficient that is 2, 2, will be now, after we take the second row minus this number multiplied by the first row, it will be, we keep only 4 digits of significance, and it will be the cancellation of these two numbers, and this is 0.0005, and I don't have other digits because I had only these two numbers. Okay. And here the 0.6452 will be now this minus the number, the coefficient that we will multiply the row by it, and multiplying the first row or the element in the first row, the corresponding element. And we'll get also some cancellation between the two numbers. They are close to each other. And now the x2 is this dividing this. Okay. Now the equation or the augmented matrix looks like this. And by backward substitution, I will say that x2 equals this dividing this, which is 1.6. And I substitute this 1.6 here and get x1 to be 12.41. So I have now the exact solution was 10 and 1. Now it's 12.41 and 1.6. So my error in x1 is 24%, and my error in x2 is 60%. Huge. That's because we divided by that small number and then added something subtracting. So what's the solution of this problem? Which is like the two problems are close to each other. The one problem is that the pivot is 0. That's an analytical problem. I have to swap. And the second problem is that it's small. I don't want it to be small or 0. It's for me the same. One is analytical and one is numerical because of rounding. So what's my way? I swap. I swap with what? With the largest one. Okay. So I avoid this problem, or I try to avoid this problem statistically in my most efficient way. So I swap. And I swap at each step or before each step. So we had step 1, step 2, step 3, okay, up to step n minus 2. So before step 1, I look at A11, A21, A31 until AN1 and choose of them the maximal one. The maximal in its magnitude, yes? First, some of them can be negative, or all of them, but I'm talking about the magnitude. I choose the row which has the bigger or the largest magnitude of that number in the first column, and I swap with it. I swap the first row with that row. And then I do my first step. Okay, I can include at that step here what you see. I can include at that step that the element on the column I want it to be 1. So I divide by that. I divide the row by that. We can do it. We can also not do it. And after I finish this first step, I then will have the second step. So before the second step, I look at A22, A32, A42. I'm looking at the second column and starting from the second row and below. And I choose the row with the A that is maximal in its magnitude. I swap with it, I swap the second row with it, and then perform my second step. Okay. So here's a simple example of that. We have these two equations, and as you see, A11 is small, A21 is big, so I swap these two rows, and now my new first row is this, and my new second row is this. And after I swap them, now I can make my calculation. So this problem also have the exact solution of 10 and 1. And if I use my elimination way, getting to the upper triangle matrix, and then use that substitution, I get to x2 equals 1 and x1 equals 10 without using any question. And for amusement, let's take another example of finding the inverse matrix. And so when we start with this matrix, check this augmented matrix. Here, the first row has the biggest element at the first column between all the rows, so I don't make any swap. I will be still left with the matrix itself, and now I will take this row minus 4 to multiply by this row minus 4 to multiply by this. That's because all of these are 1s. And then I get to this 4. Now I will take this is the biggest number, so I will swap between this and this. Then divide this row by 3 because I want here 1. So I will get 1 minus 1 minus 1 minus 1 minus 1 over 12, 0, 1 over 12. I will get them here. And this row will be here now. I take minus 2 multiplied by this row after I divide it by 3. So this is an elimination that you know. And then we get our inverse matrix. Okay. Again, if you have in advance a vector B, it's better for B to be concatenated with this. to be in the augmented matrix and to make the elementary operations also for it, not to find a minus one and multiply it by it. Okay, and for you to know the computational cost for this, if you go after the calculations that we did, you have a priori you have n squared elements in the matrix, and we've done somehow n steps. You can think about this and understand why is the order of n cubed. And if you somehow enumerate these steps, you will find that the number of divisions and multiplications that you've done is this, and the number of additions or subtractions is this. And of course, this will cost the machine, any multiplication or division would cost the machine, let's say C1, it's a constant, C1 operations, let's call it, and this C2, so the overall operations or basic operations that the machine will do is this multiplied by C1 plus this multiplied by C2. At the end, it is of order of n cubed, and this is a big number, of course, n cubed, because matrices that you'll find in research, for example, if you go to research, are very big matrices, and n cubed is very. So if we have more than one B, we can somehow reduce this complexity. We'll talk about this in the next recitation. We'll talk about LU decomposition and SVD decomposition. And we will generalize also for non-square matrices. Okay. So, as I said, it's the shortest and the easiest. So that's it for today. You have the homework. Any questions? Okay. So I think because of the election, we won't have the next week station, but let's make it Friday, not this Friday, but the next day. Okay. At 8:30. And it will be also on Zoom. It will be longer than this because the material of it also you didn't know before what is LU decomposition and SVDs, yeah? Oh. So see you.